We're almost done with the complete code. However, a few important steps remain. In this lecture, we will do three things. We'll add a way to include surface tension, we'll modify the code so that the viscosities in the different fluids can be different, and we will increase the order of the time integration. First, the surface tension. The key thing about surface tension is that it is a tension. The force is parallel to the interface, and if the interface is flat, the pull on one end of a small interface segment is balanced by the pull on the other side. If, however, the interface is curved, there is a net force in the normal direction that is proportional to the curvature. For our purpose, it is important that we need the force on the part of an interface that lies within a control volume, not the force per unit area. While we may be tempted to write down the force per unit area and then multiply it by the area of the interface segment, it is better to go back to the definition of the surface tension. We can get there from the standard definition of the interface force by using that the curvature times the normal is, by definition, equal to the derivative of the tangent vector with respect to the interface length, s. The integral over the curvature times the normal over the interface segment delta s is, if sigma is constant, exactly equal to the difference in the pull on either edge times the surface tension coefficient, or the surface tension coefficient times the difference between the tangent at the edges. Thus, we only need to find tangents to the interface and not the curvature, which simplifies the computations considerably. Furthermore, we end up with a more robust algorithm that is conservative in the sense that the force on the end of one segment is exactly equal and opposite to the force on the segment attached to it. This is important since for closed surfaces, the net surface force should be zero, and when we sum over all the interface elements, the forces on adjacent elements cancel. The numerical implementation is straightforward. We compute the surface force on an interface segment that consists of half the elements attached to an interface point. The tangent force that pulls on the segment to the right of point L, halfway between point L and L plus 1, is given by the difference in the coordinates of these points divided by delta S, the distance between them. Delta S is computed as the square root of the difference in the x-coordinate squared plus the difference in the y-coordinate squared. Thus, the force on the interface segment containing point L and consisting of half the element before and after the point is given by delta F equal to sigma times the tangent vector at L plus a half minus the tangent vector at L minus a half. The main consideration when transferring the force from the interface to the fixed fluid grid is that the total force must be conserved. Thus, the surface integral over the force per unit area, or length in 2 dimensions, must be equal to the volume integral over the force per unit volume, or area in 2 dimensions on the fixed grid. The total force on the interface segment that will be transferred to a given grid point is the integral over that segment. Each segment generally consists of several interface elements, and we must sum over those elements. For each element, we found the force, denoted by delta FL, on the last slide by subtracting the tangent. On the fixed grid, we need the force per unit area in 2 dimensions, and the total force is the integral over the control volume surrounding its grid point, or F subscript I, j times delta x and delta y. The total force on a surface segment that is transferred to a given grid point must be equal to the total force on the grid. The force transferred from each element is already the integral over the element, so we just need to sum those over all elements that are close to each grid point, and to recover the force per unit volume on the fixed grid, we divide by delta x times delta y. In general, each surface element can contribute to more than one point on the fixed grid, and we divide the surface force between the different grid points based on weights W, where the subscript L denotes the element and the subscript I, j denotes the fixed grid points. Obviously, the weights for each element must add up to 1 so that the total force is accounted for. When we use a staggered grid where the different velocity components each have their own control volume, the different components of the surface force are distributed to different locations on the fixed grid. Once we have the surface force per unit volume on the grid, those can be added to the discrete Navier-Stokes equations. For the fluid flow, we can assume that a flat boundary can be represented as a symmetry boundary. Although this is mostly used for inviscid flow, we can also use it for no-slip boundaries if we add the constraint of a zero tangent velocity. We assume that the same is true if we add surface tension, so the surface tension for the boundary nodes can be set by assuming a symmetric or a ghost interface on the other side of the boundary. This results in a zero normal force by symmetry, and for bilinear interpolation, or area weighting, no adjustment is needed for the normal velocity since we are not solving for the velocity at the boundary. The tangent force at a point half a grid spacing away from the boundary has to be modified by adding the contribution from the ghost interface on the other side. The addition to our code is relatively simple and consists mostly of lines needed to transfer the force from the front to the grid. Since the x component goes to the points where the u velocity is stored, and the y component goes to the points where the v velocity is stored, we need separate lines of code for the transfer of each component. Here we find the tangent vector in the first for loop and distribute the force to the grid in the second loop. The tangent force for the boundary nodes is then corrected at the end. In general, the different fluids will have different viscosities. We started by assuming that they were the same to make the development simpler, but here we extend the code to fluids with different viscosities. We do, however, assume that the viscosity in each fluid remains constant, as the densities do. The main change is that we need to include the full deformation tensor, so the viscous stresses are now given by the surface integral of the viscosity times the full rate of deformation tensor dotted into the normal. The deformation tensor is a symmetric part of the velocity gradient tensor, obtained by adding the tensor to its transpose, and for two-dimensional flow we have three independent components since the off-diagonal terms are the same. Since we are working with values per unit volume, we need to divide by the volume of the contour volume. For rectangular contour volumes, the normal on each side has only one non-zero component. The integral is approximated by the midpoint rule for each side, and since the normal on each side has only one non-zero component, only one part of the deformation tensor appears on each side. For the x component of the viscous stresses, the first part results from integrating over the vertical boundaries, giving the difference in the viscosity times the rate of change of the u velocity in the x direction on the left and the right boundary times delta y, and the second part gives the difference in the viscosity times the sum of the y derivative of u and the x derivative of v on the top and bottom times delta x. Similarly, the y component of the viscous stresses consists of the difference in the viscosity times the sum of the x derivative of v and the y derivative of u on the left and right times delta y, plus the difference in the viscosity times the rate of change of the v velocity in the y direction on the top and bottom boundary times delta x. Approximating the velocity gradients by center differences, we find that the staggered grid provides the various velocity component exactly where we need them. For the u component, we need the x derivative of the u velocity on the left and right boundary, and on the top and bottom, we need the y derivative of u and the x derivative of v. The viscosity, however, is given at the center of the pressure control volume, which works fine for the left and the right boundary, but for the top and the bottom we need to interpolate from the four surrounding pressure control volume. Similarly, the v component is given by approximating the velocity gradients by center differences, and again we find that the velocity components are given where we need them, but that we need to interpolate the viscosity on the left and the right boundary. The modified code for the viscous terms is a little longer than for the simplified version, but the structure is the same. We do each component separately since the number of grid points is different for the u and the v velocities, and here we interpolate the viscosity directly in the expression for the viscous terms. Since some of those are the same, we could have pre-computed them at the cost of adding storage. Since the viscosity is different in the different fluids, it needs to be reset as the interface moves, just as the density. Although we really only need to visit points close to the interface, since those are the only ones that change, here we loop over all the grid points to keep the code simple. We started by using a one-sided approximation for the time derivative, where the quantity that we are revolving at the next time level is given by the current value plus the right-hand side, or the rate of change of the variable with time, multiplied by dt. This results in a method, often referred to as the Euler method, that is only first order in time. This is usually not sufficiently accurate for serious computations. The simplest way to make the time integration higher order is to use a two-step predictor corrector method, sometimes called Hund's method. It's easily shown that we can write the method as two first-order Euler steps, followed by an averaging of the initial and final value. However, we can do a little better with almost no effort, and here we will implement a third-order Runge-Kutta method in a very similar way. To simplify the notation, we use the shorthand du over dt equal to L of u for the Navier-Stokes equations. The third-order Runge-Kutta method used here is usually written as 3 steps. First, we do a simple Euler steps where the right-hand side is multiplied by dt and added to the old value. Then we compute the right-hand side using the new velocity and add it to a weighted sum of the original and new velocity, and then we do the same thing again. As written here, we have to store the intermediate velocities as each step. We can, however, rewrite it where that's not necessary. First, we rewrite the steps as shown in the bottom part of the slide, where each new velocity is written as a weighted sum of an Euler step and the original velocity. Using this rewrite, it's easily seen that we can split each of the steps on the last slide into an Euler step followed by a weighted average with the original velocity at the nth step. Using this rewrite, the conversion of our code from a first-order explicit code to a third-order explicit code is very simple. We simply take 3 first-order steps, each one of which is followed by a weighted average of the new results and the average value at the beginning of the step. The changes to the code are very minimal. In the main time integration loop, we start by storing the current velocity, and we add a loop which goes 3 times through the first-order step that we had in the original code. At the end of each pass, we average the new and the old value, and the only complication is that the averaging is different in each pass. Thus, we need an if statement to determine which averaging we should do. I note that it is important that we do not change the front during the sub-steps, and this is the reason that we have put the restructuring of the front at the end of the time step rather than right after we have moved it. We now have a fully functional code that is second-order accurate in space, third-order accurate in time, and includes surface tension and different viscosities in the different fluids. I don't really expect you to be able to read the code on this slide, but include it mainly to be able to insist that it still fits on one slide, or to show that the size is still very modest, or about 280 lines in MATLAB, including a few lines for diagnostic and post-processing of the data that I will discuss in the next lecture. The codes that we have developed can be downloaded both from the website with these lectures and also from a Dropbox site by clicking the links listed here. We use the same initial conditions as before, but set the surface tension to a finite value designed so that the drop remains nearly circular as it falls and hits the wall. Unlike the zero surface tension drop that we simulated earlier, which continued to deform as it fell, here the surface tension keeps the drop nearly circular as it falls, and it's only as it hits the bottom wall that it deforms to a significant degree. Then it bounces slightly off the wall before falling back and settling into a nearly circular shape. The code that we have produced is a complete code that is capable of producing reasonably accurate results that would have been publishable in scientific journals when it was acceptable to present results for 2-dimensional flows only. Indeed, some journals still accept such results. We can, however, improve the code in a number of ways, and after we have examined the accuracy of the results in the next lecture, we'll extend this slightly by allowing uneven spaced grid lines and incorporating a more robust scheme for the advection terms.